Oh, wait, was that me?
All right, so hi everybody, thanks for tuning in today. This week, our seminar speaker is Dr. Eva Scheller, who is currently a Heising-Simons 51 Pegasus B postdoctoral fellow at MIT. Dr. Scheller is a planetary geologist whose research focuses on characterizing geological processes on terrestrial planets to better understand their potential for habitability, either in the present or in the past. And she particularly focuses on the planet Mars. Her research is interdisciplinary, commonly combining laboratory experiments, remote sensing, machine learning, data science, and also theory. She received a bachelor's degree in geology from Copenhagen University, and then a master's and PhD in planetary science from Caltech, where she just graduated this year, so congrats on that. And during her grad study, she also got involved with the Mars 2020 Perseverance rover mission, which I know she'll be talking a little bit about today, and she's still involved with the mission. And then this fall, she just started her current position at MIT. And so let's thank the speaker again for joining us, and take it away.
Yeah, thank you so much for that introduction, and thanks for having me. Super excited to be here. So today we're going to be talking about how we can understand water on Mars through various different means. We're going to talk a lot about isotopic modeling. We're going to talk about satellite data, and we're going to talk about the Perseverance rover as well. So just a little introduction to me. I'm actually sort of in the intersection between planetary science and geochemistry. So you'll probably hear terminology from both fields. If you want to know more about my work, these are the different places that you can look up some of my work. But in general, as Francis already told you, I work on terrestrial bodies in various ways, in particular to understand their climatic evolution and habitability evolution. I have previously worked on a couple of different Mars missions, but I'm currently very active on the Perseverance rover mission, and we're gonna talk more about that later in the presentation. What we're specifically going to talk about today is two different parts of my research. We're going to talk about this paper, which is about drying of Mars and what could have caused the drying of Mars over geological time. And then we're going to talk a little bit about how we can trace liquid water environments with the Perseverance rover in the second part of the talk. So I'm by no means the only person who have studied liquid water on Mars. Even on this call, there's a lot of people who have studied that. And even if you don't study liquid water on Mars, maybe you've seen some of these different titles of articles, finding water on Mars in various different ways. And maybe you've asked yourself, you know, we kind of know that there has been liquid water on Mars. So why do we keep sort of going back to that question and trying to understand even better the conditions of the existence of this liquid water on Mars? And so in my mind, it really comes back to this question of planetary habitability. So habitability is the ability of an environment to support life. And I like to think about habitability as part of this kind of Venn diagram that has four key components here. And liquid water is one of those components, basically, providing a solvent that, you know, life as we know it on Earth, at least, needs to exist. And so in my mind, that's why we always want to go back and we want to understand liquid water in terms of how it defined Mars's habitability. Another term that I want to introduce to you is continuous planetary habitability. So we can think about habitability as just, you know, any kind of given time an environment could have been able to support life. But in this kind of term, we think about how long could the planet actually have sustained liquid water and have sustained habitable conditions. And that becomes really important because in a lot of different kinds of research, there's this sense that life on Earth at least took a really long time to form and evolve. And so maybe you need what I'll say, or what I'll call geological timescales, like billions of years you need to have these habitable conditions over billions of years in order for life to form. So that's particularly what we're going to address today. This is what I would say we know about how much water there was on Mars in different time periods. In the past, in this blue bar here, there is an estimate of there being about 100 to 1,000 meters GL of water. So I'm going to define for you what is a GL. A GL is a global equivalent layer of water. So imagine you covered the entire sphere of Mars with a 1 meter thick layer of water, then that would be 1 meter GL of water. And so that's the unit that I'm going to use throughout when I'm talking about water volumes. It's just like an easier way to talk about it rather than saying so and so many kilograms of water. So basically, we have a lot of water in the past, and then we also have some water today, about 20 to 40 meters GL of water, locked primarily in the ice deposits on Mars. So there's a sense that water levels have decreased over time, maybe illustrated here in this little more bluish Mars planet, and now it's much drier in this later stage. I find it would be fun for us to kind of step through how we actually know this from prior research. So the first way that we realized there was a lot of water on Mars in the past was really early on in the early days of NASA missions. For example, the Viking mission was able to take pictures of the Martian surface and saw that there was lots of remnants of past river channels. So this grayscale picture here is actually showing old river systems that would have needed liquid water to form on Mars. And then we got higher resolution satellite imagery that could define these river system even better and even found lake systems as well. And then there are some people who have studied even potential shorelines of oceans as well. So there's all these what we call geomorphological evidence for liquid water on Mars in the past. Now, the people who studied these different geomorphological features can use the geometry of these features to calculate a volume of water that would have been needed to form these different features. And so I've summarized some of these different types of calculations in this diagram here, showing how they end up in this kind of 100 to 1,000 meters GL range based on various different ways of calculating this. We have another piece of evidence for past liquid water on Mars, and that's our mineralogy. So, for example, the Mars Reconnaissance Orbiter has an infrared spectrometer that's able to detect what we call hydrated minerals or aqueous minerals that form directly from liquid water. They need liquid water to form. And that's what's represented in all these little symbols across the Martian surface here. You can see that a lot of these symbols are the little blue circles, which we call phyllosilicates. And those are minerals that actually contain water or H groups in their mineral structure. They actually have water in their mineral structure. Another thing that we can do with this map is we can look at how old these different minerals are. We divide the Martian geological history into 3 main periods. That's basically based on dividing the surface into numbers of craters. The idea is that if you have an older surface, it would have more craters and vice versa. So our oldest, most cratered part of the surface is called NOACHIAN mass, and that's about 4 billion years ago. And there's a middle period that's also quite ancient. It's like 3 to 3.7 billion years ago. That's called the HESPERIAN. And then the past about 3 billion years is called the Amazonian. And I'm going to be saying NOACHIAN quite a lot. So just remember, that's a really ancient part of Mars. And what you can see here is all these little symbols, which are our minerals that form from liquid water. They are all primarily in the orange and the green terrains, the really ancient NOACHIAN and HESPERIAN Martian terrains that are all 3 to 4 billion years old. So they're all really, really ancient. That's the first really sense that these hydrated minerals, there's something different about them compared to Earth because they're so ancient. Another thing that we can do with the satellite data, with rover data, and also looking at the Martian meteorites is directly calculate actually how much water is in those minerals. So I'm showing here just an example of some drill holes taken with the Curiosity rover. And all these different samples are different drill holes that have been measured for their water content on the Martian surface with the Curiosity rover. And you can see that it was found that there was about 1 to 3 weight% of water in these different materials. And so integrating all of those different ways of measuring water in the Martian ancient crust, there's a water content range of about 0.5 to 3 weight% of water in this 3 to 4 billion year old, what we call NOACHIAN and HESPERIAN crust. The other question that people have had is how deep do these different hydrated materials occur in the crust? We don't have a lot of, or we actually don't have any instrumentation for Mars that can look directly at the vertical structure and tell us how much of the deep crust is hydrated. So the best that people have been able to do is look at places where there are really large impact craters. So, you know, a really large asteroid impacted into the surface and excavated very deep into the crust. That's sort of the best that people can do in terms of looking at the deep crust so far. And what, for example, this really great study by Sun and Millikan in 2015 found was that these hydrated materials, which are in the red and blue line, occur all the way down to 7 kilometers depth in the crust. And there's a lot of other studies that kind of get similar numbers, seeing that all the way down to 10 kilometers in the crust, you can see this hydrated material. So what I'm going to do now is we know that, you know, approximately the area of the crust that has these hydrated minerals. We know what the concentration of water is in that crust, and we also have some sense of how deep that occurs. So that allows us to do some very sort of first order of magnitude volume calculations of how much water would be in this ancient NOACHIAN and HESPERIAN crust. And so using these different ranges of numbers, you would calculate that the NOACHIAN crust has about 100 to 900 meters GL of water, and the HESPERIAN crust might have had a little bit less or approximately the same amount of liquid water as well. Okay, so what about today? Today, there are radar diagrams through the poles that have shown that there are layers of water ice together with CO2 ice in the poles. And these radar diagrams have been used to calculate basically the amount of water that's present on Mars today, these 20 to 40 meters GL of water. So that's how we get to this plot that I was showing you in the beginning, that we had 100 to 1,000 meters GL of water on past Mars based on these geomorphological features and based on the hydrated mineralogy that we've seen in the crust. And the ice deposits currently have a lot less water than was there in the past. So already now we kind of have a sense that there's something different going on Mars compared to Earth. If you think about Mars, at least as we know it currently, that there has been this sort of one-way decrease in water, that's pretty different from how we think about Earth, which can have this hydrated mineral formation in the crust, just the same as Mars, but there are tectonic zones that's going to release that water again, and that water is going to go into the atmosphere again through volcanic activity, and that whole cycle is what we call volatile recycling. So I'm kind of foreshadowing a little bit, but I'm hoping that will get you to think a little bit about how important it actually, these geological processes actually are in controlling the timescales of which liquid water can exist on different terrestrial bodies. Okay, so this is the question that we're going to address in the next 20 minutes. We're going to try to answer the question of, we know this water decreased in Mars. What happened to it? Where did it go? People have actually thought about this for a long time, and previous studies suggested that the primary loss mechanism for Mars's water was atmospheric escape. There's a really good reason for thinking this, and that actually goes back to hydrogen isotopes. So if you have never thought about isotopes, I put a little picture here to remind you the difference between our normal hydrogen atom and then its deuterium isotope here, which is just, a heavier form of the other hydrogen. And so basically, if you have atmospheric escape, your lighter atoms are going to be more likely to escape. And so in this little doodle, what I'm showing is that your like hydrogen, the light version of the isotope, is going to leave into space, and your deuterium is going to stay in the atmosphere. And so you would actually expect that if you measured the ratio of how many deuterium atoms you have to hydrogen atoms, that ratio that we call D to H, that should increase if you have atmospheric escape, right? So people have measured this in a lot of different Martian materials. For the ancient Mars, we see that the D to H ratio is 2 to 4 times SMO. So that's this blue interval here. So I also want to define what is SMO. SMO just means standard mean ocean water. And so that's just a reference material that we use when we talk about isotopes. So basically, like, all the values have been normalized. So just know that that's what I'm talking about when I say all these ratios according to SMO. And then the present day interval of D to H, the present day range of D to H is 5 to 10 times SMO in this red bar here. And that's based on a lot of different measurements on ancient meteorites, ancient rocks measured with the Curiosity rover measuring directly the atmosphere on Mars today, and astronomical observations as well. So there's a lot of different work by a lot of different people. But overall, the D to H has increased for time, just like we would expect if you had atmospheric escape. So that's kind of why we find that atmospheric escape has a really important role to play in Mars's water loss. If you model Mars's water loss only with atmospheric escape, what you'll find is that there are some little issues. So here I've summarized some of these previous studies that have done this, and they basically show that you can account for the loss of 10 to 200 meters GL of water. So kind of in the lower end of what we expect to have been lost on Mars. The other thing is there is actually instrumentation that had measured how much hydrogen is being lost from Mars's exosphere today. And those hydrogen escape rates or escape fluxes are actually really low. So if you were to integrate those rates over the whole 4 billion years of Mars's history, you would end up with about 10 to 20 meters GL of escape. And that's what this red bar is showing here. So in order to explain even these blue bars of atmospheric escape, which are still in the lower end of what we kind of think there is based on geological observations, the hydrogen escape flux would have had to be much higher in Mars's past than it is today to explain those. This is the kind of model that people use in this study. So basically what you can do is you can sort of approximate the entire sort of surface reservoir of water on Mars, the atmosphere, liquid water, and ice as a single reservoir with a single value, because we don't have enough data to kind of differentiate between these. And that's what we kind of call the exchangeable reservoir here. And you can imagine that that exchangeable reservoir has a loss, a sink, which is the water going into space for this atmospheric escape. And it's also going to have an input, which is this volcanic degassing of water, because volcanoes degas a lot of water into the atmosphere. And so that's how people have modeled this system. Now, what I'm going to propose is that maybe this is a different way of thinking of this problem. We know that we have our volcanic degassing of water. We know that we have our atmospheric escape of water. But we also know that we have a huge amount of these aqueous minerals and hydrated minerals forming at the same time, forming what I'm going to call the crustal water reservoir, which I propose that we should think about as sort of the structural water in all these minerals that are being locked inside the crust. And that happens in the NOACHIan and in the HESPERIAN. And for the Amazonian, we're going to assume that not much is happening with this hydrated mineral formation, and most of it has formed based on just the different ages of these hydrated minerals that people have been able to observe on the Martian surface. So if I were to modify this model, I would basically add another sink term, which is this crustal water, the formation of these hydrated minerals, separating a large part of the water from the exchangeable water reservoir. And then I would also incorporate these three different time periods into this kind of D2H model. And so, so that's basically, you know, just a new sort of model methodology of thinking about this problem. And so in the next 10-ish slides, I'm going to step through how this model actually works for those of you who are, you know, more interested in modeling isotopic evolution of planets, but it is going to be a little bit more technical. But I do promise you that in about 10 slides, we're going to come back and it's going to be a little bit lower level and we're going to look at the results. But this is more for the planetary scientists in the audience. So the first thing I want to show is what's going to happen when you have hydrated mineral form. How is that going to affect the D2H of Mars? For that, you need to know how we actually model isotopic fractionations. It's actually pretty simple in this case. This equation is not too important. What I want to show you is that when you model this D2H ratio, it's going to be dependent on what's called the residual fraction of the exchangeable reservoir. So basically, how much of the exchangeable reservoir is left. When you have crustal hydration, that's going to remove a lot of water from the exchangeable reservoir. That's kind of what we talked about in the previous slide. And so that's going to totally change this parameter here, and it's going to change the D2H. So that's why I'm proposing that it's going to really have a big effect on how we think about the D2H evolution of Mars. So what we're going to do is use these order of magnitude calculations for different water volumes in the ancient crust of Mars to see how that's actually going to affect the D2H. So you can see here that in the model, we have a range of different parameters pertaining to the crustal water, volcanic degassing, atmospheric escape, some time parameters related to these time periods, and then our initial conditions. And so here you can see a plot of the D2H of this exchangeable reservoir through geological time. And in this plot, we keep all these other parameters constant, and we vary only this crustal water reservoir size. And we're going to look at the other parameters in a moment, but let's just focus on the crustal reservoir size first. What you can see clearly is that just varying this reservoir size really has an effect on the model D2H, right? Like these 4 different lines are pretty different, and that's from just changing the crustal hydration reservoir size. If we go into a little bit more detail, what's actually driving the differences in these lines is how much hydration you have of the crust in the NOACHIan and the HESPERIAN period. So in the solid versus the stippled line, you have more crustal hydration in the solid line, and that causes a larger upturn in D2H. In the difference between the dark green and the light green line, you have a large amount of hydration in the HESPERIAN period. And if you have more hydration happening in the HESPERIAN, you're going to have less hydration happening in the NOACHIan. So that's why the D2H is lower here. So there's kind of a trade-off there. Then we're going to look at the volcanic degassing effect on D2H. And basically, igneous materials, D2H, has been measured in a lot of Martian meteorites, and they generally have a very low D2H compared to the Martian atmosphere. So if you imagine that you have this very low D2H gas and you're mixing that in with your higher value exchangeable reservoir, overall the exchangeable reservoir is going to decrease because you are mixing in something with a lower value. Now, we're not performing any kind of volcanic modeling in this study, but we rely on some previous studies by Grodial 2011 and 2013, which are still sort of the most current volcanic degassing models for Mars. And they have quite a range of possible scenarios that could have happened on Mars, depending on different assumptions on parameters that control this volcanic degassing. One of the assumptions that matter a lot to these volcanic degassing models is how much water you start out with in the mantle. So if you have more water in the mantle on Mars, you're going to have more outgassing. Another thing that matters a lot is your assumption of whether the degassing is happening on a global scale or it's happening in like concentrated mantle plumes. And so that's what's giving rise to these different line shapes and amounts of volcanic degassing. So we're going to use these 4 different curves and vary some of our volcanic degassing parameters, keeping the rest constant. And so here in these different line colors that correspond to the 4 volcanic models from before, the takeaway is that if you have a low amount of volcanic degassing, then your D to H is going to constantly upturn. It's not going to decrease at any point because you don't have enough gas to make it really decrease on a global scale. But if you have a lot of volcanic degassing, you can actually cause your D to H to decrease because of all this low D to H gas that you're mixing in to the atmosphere. So those models actually end up being really important for how the D to H evolution of Mars ends up being. And at least at present, we can't really differentiate between which of these lines the real Mars actually took. Then the last sort of important mechanism for this model is, of course, the atmospheric escape. We've kind of already gone over that. If you have a higher hydrogen escape flux, that's going to increase your D to H more because you're removing more of the lighter hydrogen. And so this ratio is going to, of course, increase. Now, the really big question, though, is like, what is the hydrogen escape flux of past Mars? For the Amazonian, we can maybe assume that it's similar to the modern rate, which is this 5 × 10⁻26 hydrogen per second. But it's really a big question what it was in the NOACHIAN and HESPERIAN, because it really depends on what the atmospheric structure was on Mars in the past. And I had some help from my collaborators at Caltech and JPL, Danica Adams, Professor Yok Young, and Dr. Renyu Hyo, who were able to model this for us in the study using their photochemical atmosphere software called Kinetics, which is very cool software that can do all the like photochemistry that's involved in calculating different scenarios of hydrogen escape fluxes. Basically, what they did was look at different surface pressures. So basically, thicker or smaller atmosphere scenarios on Mars. And they saw that if you have a higher surface pressure, so like a thicker atmosphere, your hydrogen escape flux would be much lower because the hydrogen has to go through much more material to get to the top of the atmosphere. But what if you took the hydrogen from the surface and then you moved it up to the top of the atmosphere? Then it's going to have a much easier time escaping. That's what this middle scenario is showing. And you can see that the hydrogen escape flux is much higher compared to not having that mechanism. And of course, that mechanism is convection, which is what we have on Earth's atmosphere. But it's a big question of whether we had that on Mars as well. The other thing you can have is geological mechanisms that produce hydrogen. There are actually a lot of different geological processes that can produce hydrogen. So if you are pumping more hydrogen into the atmosphere, your hydrogen escape flux will also increase. That's what they're showing here in the end part. So at the end of all this simulation work, it turns out that for the NOACHIAN and HESPERIAN hydrogen escape flux, there's a really large possible range, ranging actually over 4 orders of magnitude here, for depending on what the structure of Mars's atmosphere would have been. So what we're going to do for the case of my simulation here is, well, so we've looked at all these different ranges of parameters that go into the model, and we're going to vary all of those. And then we're going to look at which simulations can actually produce the conditions that we know occurred from Mars. Like we know Mars 4 billion years ago had a D2H of 2 to 4 times SMO. Now it has a D2H of 5 to 10 times SMO. And now it also has a water layer that's about 20 to 40 meters GL of water. We're going to only look at the simulations that can produce those constraints. And we're going to look at the combination of HESPERIAN escape fluxes and NOACHIAN escape fluxes that can produce those simulations while varying all these other parameters. The solution space that we end up with looks like this, like in this purple outline here. If you have more HESPERIAN and NOACHIAN escape than this bar here, your D2H of today would be way too high. If you had a smaller amount of HESPERIAN and NOACHIAN escape, your D2H would be way too low. But there's kind of a lot of possible scenarios in this purple box, basically. What is really interesting, though, is that there are some scenarios like here in this purple box where the HESPERIAN and NOACHIAN escape fluxes actually are very low. They're actually the same as today. And even those simulations can actually explain the D2H evolution of Mars when you include also this crustal water reservoir of water forming on Mars. So what we can do is like look at this simulation space and just look at one simulation where the amount of atmospheric escape is really low and one simulation where it's really high. And I'm going to show you the evolution of these reservoir sizes in percentage for the crustal reservoir and the escaped amount of water, and then the water that's still left in the surface system on Mars. And so you can see here, in this case, the atmospheric escape is actually so low. It's only like 1% of the water loss, and 99% of the water loss is due to these hydrated minerals forming in this crustal reservoir of water forming. In the other scenario, it's more of like a split scenario where 70% of the water is lost due to this atmospheric escape and 30% is lost due to the crustal reservoir. So in either case, the crustal reservoir ends up playing a big role in Mars's water loss, and it may even have been the most important reason for Mars's water loss. And then the last thing we can do is we can look at all these different simulations and try to look at how much water can we simulate in our 3 different time periods, our NOACHIAN, HESPERIAN, and Amazonian time periods for Mars's geological history. What we end up seeing is that we can actually reproduce really large water volumes. For comparison, I'm showing what the previous studies that modeled atmospheric escape could produce. And so we actually see simulations of 100 to 1500 meters GL of water. I would say more higher and also more like what the geological observations were suggesting would have been on past Mars. And then we see that decrease through these different geological periods. By the time we reach the last Amazonian period, here these past 3 billion years, the water levels are pretty low and constant throughout because we've shut off this hydrated mineral formation and this crustal reservoir of water forming. And basically there's just a little bit of volcanic degassing and a little bit of atmospheric escape that pretty much counter each other. So going back to this planetary habitability question, why do I think this is important for Mars's habitability? I think it's important because if you think about the role of this crustal reservoir of water forming from these hydrated minerals, I would call that an irreversible crustal sink. It's basically like a one-way net drawdown of water overall globally on Mars, which is very different from this volatile recycling mechanism that we have on Earth. And I think that really controls these 2 terrestrial planets' ability to have water available in their geological systems. And so basically Mars drying out very early on, I would expect is an effect of this irreversible crustal sink of water. So we're going to talk a little bit more about liquid water and the Perseverance rover. but I wanted to summarize the different points that we've gone through here in the first part of the talk, which is that drying of Mars was caused at least in large part because of this water being drawn down into the crust and forming all these hydrated minerals. And if you do model this in this kind of isotopic way, then incorporating that phenomenon actually provides a solution for some previous discrepancies in the literature regarding these models. Another really important thing is that would mean that most of Mars's liquid water occurred primarily in the early parts, like in the first like basically 3 to 4 billion years ago. And it was pretty much dry for the rest of geological history. And so thinking more about, what can we, how is this going to be important in future? It may be that because we have this irreversible crustal sink, Mars gets on a totally different path for habitability and climatic evolution compared to Earth, which always has recycling of its water. Okay, so now we're going to talk a little bit more about how we can actually look at these liquid water systems in a very detailed way. Instead of thinking about these global systems, you can really do microscale analyses with the Perseverance rover that landed in February 2021. And I saw that you guys have had a few presentations on the Perseverance rover already. But I'm gonna just rehash the different goals of the Perseverance rover very quickly for those of you who may not have been at those previous presentations. But basically what the Perseverance rover is going to do is it's gonna look at the different geological activity there's been in the landing site. It's going to try to understand if there's any kind of astrobiological material in the landing site, and then it's going to sample materials from the landing site that are going to be sent back to Earth through a 3-part NASA and ESA combined mission. So eventually we're going to have these materials in the laboratories on Earth, hopefully. So going back to this habitability diagram, why do I think the Perseverance rover is really cool in terms of understanding this? It's because it can actually address all the 4 parts of the habitability Venn diagram. In the beginning, we were only talking about liquid water, one of the 4 parts, but the Perseverance rover can look for, these required elements, organic compounds, specific physical chemical conditions in the liquid water systems, and so on. So that's really what we're going to address with the work we're doing with the Perseverance rover. Okay, so I work on the ARM instruments on the Perseverance rover. In particular, we're going to talk about SHERLOC, which is what I spend most of my time working on. The Perseverance rover, of course, is a huge team of people. So all the different data that I'm going to show you is from this entire giant group that I can't acknowledge everyone that has been a part of creating all this fantastic data. This is an artist's illustration of what the Perseverance landing site would have looked like in the past. It's thought to have been an ancient lake system in a crater that's called the Scheller crater. And what's more is that there was an ancient river that ran into this lake system. And when you have a river running into a lake, you will form what's called a delta. Some of you may have heard about like the Mississippi Delta or something like that, where basically if you have this change in the velocity of the water, you're going to settle out a lot of sand grains and sediments in that kind of form in a triangular shape. And that's what's called a delta. What's furthermore really interesting is that outside the crater, that's where this 3 to 4 billion year old hydrated crust actually is. So eventually the Perseverance rover is going to be able to make measurements and to constrain all of those things that I was talking about in the first part of the talk, but we just haven't gotten there yet. So we haven't been able to make those measurements yet. So far, we've been focusing on this crater floor, which is the bottom of this Scheller crater. And then we've just gotten to this delta part of the crater as well. And so this is what a satellite image of that crater would look like. So imagine you took all the water away from this crater and that's what you would be left with. And so the white line here is showing where the rover has been driving so far, going through the crater floor to the delta over here. And all these little purple triangles are different measurements that the SHERLOC instrument has performed. What's important just to mention is that there's actually two different kinds of material in the crater floor that we're going to be talking about. There is the CETA formation and then the mass formation, which are just two different names for two different kinds of chemical composition of rocks, basically. Okay, so before we dive into the data, I wanted to show you just one of the really early pictures of, Perseverance panorama view. The delta is really far away in the horizon. And so I feel like this kind of gives a sense of how far we've actually driven all the way, well, now all the way over here in the far distance of this picture. And we've been measuring all of these little rocks that are outcropping here on the crater floor. And that's what we're going to be talking about. Of course, the goals with measuring all of these crater floor materials were to understand whether there were any kinds of habitable environment preserved here, any kinds of biosignatures, and also trying to understand what kinds of geological processes shaped the crater floor of the Scheller crater and whether there was any kind of aqueous activity, again, trying to trace these habitable conditions, but also just understand fundamentally the geological processes that shaped this ancient lake system on Mars. So we actually knew a little bit before we landed. We have these infrared spectroscopy measurements of the Martian surface from Martian satellites. I mentioned that briefly early on. And this is the kind of data that you retrieve from those satellites, basically showing a mineral map of 3 different types of minerals in the Scheller crater. And the crater floor consists of this red part here and then also this blue part here. The red part is red because it contains olivine and carbonate minerals. So for the geologists, that will mean something. And if not, we're going to talk about it in a few slides. And then the blue part contains basaltic materials. Basalt is an igneous rock that is sort of the prime component of the Martian crust, just a really common igneous rock in the Martian crust. So already from the satellite view, we knew that we were going to see 2 very different materials. Especially the carbonate detection was really interesting for people who are thinking about liquid water because it's one of those aqueous minerals that only form if you have liquid water. And so in a review I did, I sort of summarized all the different ways we could think about these carbonates forming that are pretty unusual because they're very magnesium rich. And that's not super common for carbonates on Earth. And basically you could have had either a very magnesium and iron-rich igneous rock, which is called the Ultramafic rock, and that's one of these like olivine-containing igneous rocks. And you can have one of those igneous rocks that could have been fluid flow through that rock, and that would have formed carbonates, either in a high-temperature setting or even in a low-temperature surface setting as well. Or you could have had the carbonates formed directly from the lake water, precipitating as a carbonate from lakes, like we see many, many different lakes on Earth. So we set out to basically test these different hypotheses with the SHERLOC instrument. The way that the SHERLOC instrument works is by drilling this little circle or braiding this little circle that we call an abraded patch. And that's going to just level out the surface and make it really flat. Then we can place the arm on top of that hole, and SHERLOC is going to shoot an ultraviolet laser at the material. That's going to interact with the material and release some photons that are specifically Raman scattering and fluorescence that the instrument then detects to try to characterize the materials in the specific rock target. So we're going to look first at the results from the CETA formation. These little triangles here in the white box. In the middle, I am showing you what the Raman spectra from SHERLOC looks like. It's basically pretty noisy flight data, but you can see that there are little peaks that we're able to match with specific minerals that I'm showing up here, laboratory measurements of different types of minerals. Then what we're able to do is analyze these Raman spectra in a grid of laser points, because SHERLOC is able to do, for example, like a 10 by 10 grid of different laser shots. And that gives us spatial information of where these different minerals occur, and that helps us to interpret what's going on in the rock. The ones that I want you to focus on in this little grid interpretation of Raman spectra is the olivine, which is the green circle, which again is one of these very magnesium and iron-rich igneous materials that come from magnesium and iron-rich igneous rocks. And then in blue, the carbonate, which is that mineral that forms from liquid water. And you basically see that predominantly this is igneous, magnesium and iron-rich igneous rock, and there was some liquid water interacting with that igneous rock and forming these carbonates mixed together with the primary igneous material. So that led us to narrow down this hypothesis space to suggest that these carbonates were formed primarily by liquid water flowing through predominantly an igneous rock, and this material is predominantly an igneous rock. So yeah, we were very happy that we could narrow down this hypothesis space a little bit. What we don't know yet is whether this is a high temperature phenomenon or whether this is a low temperature phenomenon, which is what we're still working on. Then we're going to look at the mass formation, just a quick little result that I found really surprising and fun. So this is primarily a basaltic rock. Again, from the satellite, we kind of knew this was going to be basalt, and we were able to confirm that with the other instruments. But there ends up being these little white pockets of salt minerals. And when we measured them with the SHERLOC instrument, we were quite surprised to see that these are actually mixtures of sulfate minerals, which is that's a pretty common salt mineral on Mars, but also sodium perchlorate minerals. Sodium perchlorate is a pretty strange chemistry, and it's not very common on Earth. And so it turns out to actually be pretty present on Mars, at least with the different surface missions we've done. And so what we're seeing here is that there's a really intimate relationship between the sodium perchlorate and the sulfates. And so that led us to suggest that, and this is a kind of liquid water process that is forming both of these material, and it has to be a pretty late stage liquid water process, because perchlorates are super soluble. So if you had any kind of subsequent water, it would just totally erase that perchlorate structure. So this has to be at least the last instance that this part of the rock is seeing liquid water. Okay, very last, another thing that SHERLOC is able to do, and this is maybe like a primer for future work that's to come. We're not going to go too much into detail about this, but what SHERLOC can actually do is look at fluorescence signals from potential organic compounds on Mars. We basically retrieve these really broad signals that you see here attributed to fluorescence. And in some cases, like this really broad peak here, we only really know that one-ring aromatic organic compounds can produce those signals. In some cases, we know that other types of aromatic compounds can form this signal, but we also know that some inorganic compounds like cerium can form this signal. And so far we think at least this part is an evidence of one-ring aromatic organic compounds actually being present in all of these different aqueous materials. And so, but that's for another talk, another day. But that's something we're also working on with the SHERLOC instrument. So we've actually sampled all of these different rock types that I've been talking about. We're sampling the delta right now, and those rocks are set to be returned to Earth so that one day we can measure them in the laboratory, confirm these organic compound detections, and understand better the types of conditions that led to this carbonate formation and this really strange water chemistry in these different igneous rocks on Mars. So just wrapping up here, we've already kind of gone through the synthesis points for the first part of the talk, which was about drying of Mars and how it was caused in part by these hydrated minerals forming in the crust. And then we were able to look at these really cool carbonate forming alteration environments. So liquid water flowing through an igneous rock and altering its chemistry. We were able to look at really strange perchlorate and sulfate forming liquid water environments, and that some of these aqueous alteration environments also contain fluorescence, which is likely to be from aromatic organic compounds. Okay, that's all I had today, and I'm very happy to take any questions.
Awesome. Thank you so much for that great talk. I'm just going to stop the recording real quick. And